Okay, looking at or discussing what volume do you want to measure in, you have to consider what's your volume of interest, and how do you set your system up to match that volume of interest. And these are just some examples of data that we've collected in the past showing extremes in aspect ratio of your volume, going from 1:1, more of a cubic volume, to more of a plane volume, more like what you have for stereo PIV, but trying to improve the accuracy using tomographic PIV. So considering the volume that you want to measure in, you have to consider what are your depth of field limitations. How do you achieve good focus throughout your whole measurement volume to ensure that you can make measurements in that volume. Now the graphs that are shown on this slide here, I apologize that the font is a little bit small so you can't see it in the back, but this is the front and back depth of field relative to your center plane for two different focal length camera lenses. So your depth of field is dependent on the focal length of the lens that you're using, and you can note that you can use any type of lens for your setup. You're not restricted to a particular type of lens, for instance. Also dependent on your stand-up distance. How far away are you from your measurement volume? Of course, your f-stop. So each one of these lines here is for a different f-stop, ranging from the black is f4, and the green is f16. So as you might expect, or as you well know, the depth of field increases as you close the f-stop. Also, where is the edge of your depth of field? This is determined by your tolerance for how out of focus can a particle on an object be, and this is sometimes dubbed the circle of confusion. I love that term. One thing to note, when looking at these two examples here, this is a 50 millimeter lens on the left and a 100 millimeter lens on the right, is that the ratio of the area to depth of field is a constant. Okay? So if you've got a certain depth of field that you want to achieve with a particular lens, you can be closer to that object with a shorter focal length lens versus a longer focal length lens. And I'll touch upon that later, why that's important to consider, what focal length lens that you're using. Always a good way to check to see, okay, this is theory, but when you're checking your full system, if you've got time and the capability to move your laser, is to create a thin light sheet and take images of that light sheet at the extremes of your volume to make sure that the particles that are in focus at those extreme dimensions. Now, as I mentioned earlier, any lens, any type of lens can be used on your system. These are just normally using standard F-mount lenses. But there are some recommendations. Use fixed focal length lenses. They're simpler. There's less lens elements, so that leads to less distortion and also larger apertures, smaller F numbers. And all things being created equal, if you can, use a shorter focal length lens to reduce your your standoff distance. Now, you can draw an analogy if anybody plays golf. If you're using a short range iron, usually it's more accurate than using a driver, at least in my golf game. So when the cameras are further away from the object, with a longer focal length lens, if there's any movement of anything in your system, that's going to translate into a longer, it's a larger optical moment, and you'll have larger pixel movement on your array, which will lead to higher errors, which are harder to